Hello everyone, this is Asha here. So today we are going to discuss about the topic Einstein theory of photoelectric emission, which is there in atomic structure and elementary quantum mechanics. So under this topic or under this theory, we have to discuss that this theory was first put forward by the scientist Einstein in the year 1905, and he had proposed this theory based on the Planck's quantum theory of radiation. So, as we know, Planck's quantum theory of radiation says that the energy present in the discontinuous form, that is, in the form of short packets of energy, which are also called as quanta, or you can call as photon. So, according to this quantum theory, the light consists of a tiny bundles of energy, which is called as quanta or photons. So as we know, the energy equation for a photon, which is equal to h nu, where h stands for the Planck's constant and nu stands for the frequency of light. So overall, the energy equation will be E is equal to h nu. So as we know, the photoelectric effect is nothing but the if a photon of energy of frequency strikes the metal atom, therefore its energy will be consumed in two ways. So since we know the photoelectric effect is nothing but the emission of the light radiation on the metallic surface leads to eject the electron, right? So the ejected electron is called as photoelectron, and the particular phenomenon is called as photoelectric effect. Now, as in photoelectric effect, the energy involves like energy is consumed in two ways. In that, the first one is a part of its energy will be used up in removing the electron from the surface, and the other particular amount of energy which is used up is depends upon the nature of the metal, which is called as the work function. And this work function is generally represented with a symbol phi naught. So in simple words, you can say some part of energy is required to remove the electron from the metallic surface or for the ejection of the electron. So this energy depends upon the nature of the metal, which is called as the work function. And the next point is the remaining part of the energy of striking the photon will be used up in imparting the kinetic energy to the ejected electron. Or in simple words, you can say that the remaining part of the energy is used to impart the kinetic energy. Kinetic energy whose formula or whose equation is equal to 1 by 2 mv square. So from the total amount of the energy, right, we have to consume in two ways. First way is that the energy required to remove the electron is called as the work function, and the remaining part of the energy is used to impart the kinetic energy. Now, based on these two types of consumption of energy, we'll solve one or will do or will derive one small derivation. Where, as we know, the energy equation that is E is equal to h nu, right? E is equal to h nu, and the just now we have seen energy can be consumed in two ways. So in first way, the energy which is required to remove the electron is called as the work function, which is represented with a phi naught. And here this is a work function, not a wave function. This is called as the work function. Now the energy equation, right? That is h nu is equal to phi naught plus 1 by 2 mv square. So now here you may get a doubt how we got this energy equation. So since we know the energy equation that is E is equal to h nu. Now here in this particular process we have seen that the energy consumed in two ways. First one is it is for the work function which is represented with a phi naught, and The remaining part of the energy is used to impart the kinetic energy, whose formula is half mv square. So the energy which is required to remove the electron is called a work function, and the remaining energy is called as a kinetic energy, right? So to calculate the total amount of the energy, we need to add up both the energy. So that's what I have represented in the first equation. That is h nu is equal to phi naught plus 1 by 2 mv square, where phi naught is called a work function. And since we know the kinetic energy formula, that is 1 by 2 mv square, right? This information already we know. Kinetic energy formula and the energy equation. Now, here the work function which we have used, right, which is equal to h nu naught. So this nu naught is called as your threshold frequency. Now, this particular data, let's number this as a equation number 1 and let's take this as a equation number 2, right, for just for consideration. So just what we need to do, once we get the phi naught value is equal to h nu naught, you need to substitute this equation number 2 in equation number 1, where you are having the phi naught value, right? Just you need to replace over here. So here on substitution, you'll get the equation as h nu is equal to, in the place of phi naught, what we need to substitute, that is equation number 2, that which is equal to h nu naught. Therefore, h nu is equal to h nu naught plus 1 by 2 mv square. Just we had substituted equation number 2 in equation number 1. So now we need to simplify it. So here when you go for the simplification, just you need to shift this term toward this side. That is h nu naught, which was plus. When you shift toward left side, it becomes minus. Therefore, you will get the equation over here as 1 by 2 mv square, that is kinetic energy, is equal to h nu, and as we are shifting toward this side, it becomes minus. Therefore, minus h nu naught. So now here the common term is h, right? So here on simplification, you'll get 1 by 2 mv square, h is common, so just take it aside, is to nu minus mu naught. Right, that's what I have written over here. That is 1 by 2 mv square is equal to h is to mu minus mu naught. So this particular equation, just number as equation number 3. So this equation is called as Einstein photoelectric equation. So how we got this equation? First, we have considered the energy equation, and there are two conceptions of energy, two forms of energy. That is the energy which is required to remove an electron and the remaining part of the energy. You just need to add up. And here you have to consider phi naught is equal to mu naught, h nu naught. Next step, you need to substitute this value in equation number 1. Therefore, on substitution, you'll get the kinetic energy equation, that is 1 by 2 mv square is equal to h is to nu minus mu naught. So this particular equation is called as the photoelectric equation. So here in this particular theory, one you have to make a note. So this theory, like the photoelectric effect, can be explained if the light radiation is supposed to have a particle nature. As we know, light is having a dual character, right? It can have a wave nature or a particle nature. So this photoelectric effect is possible only when the light radiation have a particle nature. That is, particle nature means the light is present in a discontinuous form, or you can say the short packets of energy, or in the form of quanta. Then only this Einstein theory of photoelectric effect is possible. I hope it's clear. So we'll see the quantum effect in the next in our next classes. Thank you for listening.